This video is going to continue our study of inverse functions and look at some of the technical issues that come up. Inverse functions have a job to do, and then they also need to satisfy the definition of a function. And these two requirements sometimes run into conflicts with one another, and we have to kind of be very careful to see which one comes into play. So let me give you an example. So f of x is equal to x squared. What I want to be able to do is I want to be able to take this function f and I want to be able to pair it with its inverse to cancel out the action of the function. All right? And if we look at something like this graphically, we find that the inverse function satisfies a certain property, or it satisfies a certain symmetry. If I draw in a function, let's say I just draw a shallow line, and let's say that this is f is equal to x over 2. Okay, it's going to turn out that if I find the inverse function for this, that inverse function is going to be 2x. Okay? And if I draw that inverse function in, what I see is that the inverse function is actually a reflection of the original function across the line y equals x, or x equals y. Okay? X equals y is the identity function, and when I look at the function, the inputs lie on the horizontal axis, and the outputs lie on the vertical axis. Okay? So when we switch the roles of the inputs and outputs for the inverse function, we end up flipping the graph over the line y is equal to x. We turn things over. So this side, in this graph that I've drawn here, this is f, is this lower line, and f inverse is this upper line. Okay? So there's kind of a graphical correspondence between a function and its inverse. They're reflections over the line y is equal to x. And the reason that reflection is because they switch the roles of inputs and outputs. If we look at f of x is equal to x squared and think back to some of the properties of the graphs of functions, we can see that we might run into some issues here. So let's draw a graph of x squared. Let's say that this is our graph of x squared. And let me draw in this line y equals x. And let me try and draw the reflection of that across the line y is equal to x. So I want to switch the roles of y and x for this graph. If I do that, I should reflect everything across this line. So I'm drawing in pink here. And here's that. This is the right side of the parabola, and then the other side of the parabola is going to be down here. Okay. Not the best picture in the world, but we'll work with it. Okay. Now, here's the problem. If I look at this graphical picture, this idea that the inverse is a flip, a reflection of the original graph across the line y equals x, that picture makes me a little bit nervous. And the reason I'm nervous is that the picture of that reflected graph, that graph of the inverse, that doesn't satisfy the vertical line test that we deduced about functions. All right, so if I look at that reflection as a whole, for certain inputs, there are two possible outputs, which means that that graph as a whole cannot be the graph of a function of x. It doesn't work as a function because it's not dependable. It doesn't take each x and return only a unique y, a single y for each x. So the way that we end up dealing with this problem in mathematics is by kind of narrowing our gaze, reducing the domain of the function so that we remove any of these problems. So for x squared, what we do is we eliminate the left side of the parabola. That's not to say that we don't say that it exists or pretend it's not there. We just restrict the domain of the function, the possible inputs, so that we leave out the parts that are going to cause problems with the inverse. Right? So if I remove the left side of the parabola there, if I remove all the negative values from the domain, then the bottom branch here disappears as well, and I end up with a smaller piece where the inverse is well defined. It does satisfy the vertical line test. Okay? And this is why when we look at the square root function, the domain of the square root function is x is greater than or equal to 0. Okay? So it's only defined for those larger numbers. When we have situations where we're trying to solve equations that involve squares, sometimes we use a plus or minus sign to cover the case that the squaring function, it actually has a left-hand side. But the inverse function is only defined on a smaller domain. Okay? So this is something that comes up into play in general, that in order to have an inverse function, a function must be one-to-one. It must only use its output values once. It can't use an output value more than once. Or you can't recover any information or unique information about the input that produced that output. An extreme example of this would be a constant function. With a constant function, you lose all information about the input because every output is the same. So constant functions have no inverses whatsoever. There's no way to extract information about the inverse of a constant function. Okay, there isn't an inverse function for a constant function. Okay, so that's kind of a basic idea about how you handle inverses in general. You have this graphical representation of an inverse, that it's a flip of the original function across the line y is equal to x, or a reflection of the function across the line y is equal to x. And in situations where that reflection does not satisfy the vertical line test, we usually handle that by restricting the domain, eliminating parts of the function that are causing problems, and then only looking at the portions that are left over.